Scalar product of standard unit vectors. Welcome, everyone. Today, we are going to dive into a fundamental concept in vector algebra, the scalar product of standard unit vectors. To start off, let's set the stage. When we study vector algebra, we aren't just working in a flat, two-dimensional plane. We are often representing vectors within a three-dimensional coordinate system. Now, working in three dimensions can get quite complex. So to make our calculations much more efficient and organized, we use what we call standard unit vectors that lie directly along the x, y, and z axes. You will see these represented by the special notation I hat, j hat, and k hat. These little hats tell us we are dealing with vectors of a specific magnitude, and as we move through the next few slides, we will explore exactly how these vectors interact with one another through the scalar product. Properties of standard unit vectors. First, it is essential to understand what we mean by the term unit vector. By definition, a unit vector is simply a vector whose magnitude, or its length, is exactly 1. Applying this to our notation from the previous slide, this means that the magnitude of I hat, the magnitude of j hat, and the magnitude of k hat are all equal to 1. Finally, we must consider how these vectors relate to one another in space. Because these vectors lie along the x, y, and z axes, and these axes are mutually perpendicular, the angle between any two different unit vectors is always 90 degrees, which can also be expressed as pi over 2 radians. Keeping this 90-degree relationship in mind will be crucial when we apply the general formula for the scalar product in the next slide. Now that we have introduced our standard unit vectors, let's look closer at their specific properties on this second slide. General definition of scalar product. As you can see on the slide, the formula for the dot product of vector A and vector B is equal to the magnitude of vector A, multiplied by the magnitude of vector B, all multiplied by the cosine of the angle theta between them. We will be using this exact formula in the next few slides to derive exactly what happens when we multiply these unit vectors together. Now that we have identified our standard unit vectors, \hat I dollar, \hat j dollar, and \hat k dollar, we need a way to actually calculate their products. To do this, we don't need to learn a brand new rule. Instead, we simply refer back to the general definition of the scalar product that you should already be familiar with. Scalar product of a unit vector with itself. Now that we have established the general definition of the scalar product from the previous slide, let's apply it to a specific case. What happens when we take the scalar product of a unit vector with itself? Think about it this way. If you are looking at the exact same vector, there is no difference in direction, which means the angle theta between the vector and itself is 0 degrees. Let's walk through a step-by-step derivation for I hat dot I hat to see how this works mathematically. First, we identify the magnitudes. As we learned in the previous slide, because these are standard unit vectors, the magnitude of I hat is 1, and the magnitude of the second I hat is also 1. Second, we identify the angle. Since the two vectors are identical, the angle theta is 0 degrees. Third, we apply our general formula. I hat dot I hat equals the magnitude of I hat times the magnitude of I hat times the cosine of theta. Fourth, we substitute our known values into the equation. This gives us 1 times 1 times the cosine of 0 degrees. Since the cosine of 0 degrees is 1, our equation becomes 1 times 1 times 1. Finally, our result is that I hat dot I hat equals 1. It is important to note that this same logic applies perfectly to our other standard unit vectors as well. Therefore, j hat dot j hat equals 1, and k hat dot k hat also equals 1. This sets the stage for our next slide, where we will see what happens when the vectors are pointing in different, perpendicular directions. Scalar product of two different unit vectors. Now that we've seen what happens when a unit vector is multiplied by itself, let's look at the opposite case. What happens when we calculate the scalar product of two different standard unit vectors? As we discussed in the previous slides, these vectors lie along the x, y, and z axes, which are all mutually perpendicular. This means that if we pick any two different vectors, like I and j, the angle theta between them is exactly 90 degrees. Let's walk through a step-by-step derivation for the dot product of I dot j to see how this works in practice. First, we identify the magnitudes. From our earlier definition of unit vectors, we know that the magnitude of I is 1, and the magnitude of j is also 1. Second, we identify the angle. Because the x-axis and the y-axis are perpendicular, our angle theta is 90 degrees. Third, we apply the general formula for the scalar product that we saw on slide 3. This gives us I dot j equals the magnitude of I times the magnitude of j times the cosine of 90 degrees. Fourth, we substitute our known values into the equation. This becomes 1 times the cosine of 90 degrees. Since the cosine of 90 degrees is 0, the entire expression simplifies significantly. And finally, our result is that I dot j equals 0. It is important to realize that this same logic applies to every other pair of different unit vectors. Because the axes are all perpendicular to one another, j dot k equals 0, and k dot I also equals 0. Essentially, whenever the vectors are pointing in different directions along these axes, their scalar product will always vanish to 0. Real-world analogy: the corner of a room. Now, I know these mathematical derivations can feel a bit abstract, so let's step away from the formulas for a moment and look at a real-world analogy to help this concept stick. Imagine you are standing right in the corner of a rectangular room. This corner is the perfect place to visualize our three-dimensional coordinate system. Look down at the floor. The line where the floor meets the first wall can be thought of as our x-axis, which we represent with the unit vector I hat. Now, look at the other line on the floor, where the floor meets the second wall. That is our y-axis, or j hat. Finally, look straight up at the vertical line where those two walls meet. That vertical edge represents our z-axis, or k hat. Now, let's apply what we learned in the previous slides about the scalar product. Suppose you decide to take a step exactly along that first line on the floor, moving in the direction of I hat. Because the x-axis is perfectly perpendicular to both the y-axis and the z-axis, just like the walls of the room are perpendicular to the floor, there is absolutely no projection of your movement onto those other two directions. In other words, you aren't moving toward the other wall or up toward the ceiling at all. This is exactly why, as we saw in our derivation, the scalar product of different unit vectors equals 0. However, if you look at your movement along that same x-axis, your path is perfectly aligned with the direction of I hat itself. There is no angular difference between your path and the axis. Because you are moving perfectly parallel to the vector, the product is at its maximum value, which results in a product of 1. Keeping this visual in mind will make the algebraic steps in our next example much more intuitive. Example: simplifying a scalar expression. Now that we have mastered the rules for multiplying unit vectors, let's put everything we've learned into practice with a concrete example. Take a look at this expression on the screen. 2i.3i plus 4j.5k. At first glance, it might look a bit cluttered, but if we follow a systematic approach, it becomes quite simple. First, let's use the property of scalar multiplication. Just like with regular numbers, we can pull the constants, the coefficients, outside of the dot product. So we group the 2 and the 3 together and the 4 and the 5 together. This gives us 2 times 3 multiplied by I dot I plus 4 times 5 multiplied by j dot k. Next, let's simplify those constants to make the expression cleaner. 2 times 3 gives us 6, and 4 times 5 gives us 20. Now our expression looks much more manageable. 6 times I dot I plus 20 times j dot k. Now this is where we apply the fundamental rules we discussed in the previous slides. Remember, when a unit vector is dotted with itself, the result is 1 because the angle is 0 degrees. However, when we dot two different unit vectors like j and k, the result is 0 because they are perpendicular. So, we replace I dot I with 1 and j dot k with 0. This leaves us with 6 times 1 plus 20 times 0. Performing the final calculation, we get 6 plus 0, which equals 6. As you can see, by breaking the expression down and applying our unit vector properties, we can simplify even complex-looking vector expressions very efficiently. Before we move on to our final summary and common pitfalls, let's take a moment to ensure this process is clear. Key takeaways. First, let's look at the top row. When we take the dot product of a unit vector with itself, meaning i.i, j.j, or k.k, the result is always 1. The reason for this is that these vectors are parallel to one another, meaning the angle theta between them is 0 degrees, and as we saw in our derivation, the cosine of 0 degrees is 1. Next, let's look at the second row, which covers the cases where the vectors are different. When you calculate the dot product of any two different axes, such as i.j, j.k, or k.i, the result is always 0. This happens because these standard unit vectors are perpendicular to each other, meaning the angle theta is 90 degrees and the cosine of 90 degrees is 0. Now that we have worked through the derivations and seen a practical example, let's bring everything together with a summary table. This slide serves as your quick reference guide for the rules we've just learned. If you can memorize these two fundamental patterns, you'll be able to simplify almost any complex vector expression with ease. However, as we will see in our next slide, there are a few common pitfalls to watch out for so you don't get tripped up during exams. Common mistakes. First, be very careful not to confuse the dot product with the cross product. You might remember from our earlier discussions that the cross product of I and j results in k. However, in today's topic, we are focusing strictly on the scalar product. Remember the golden rule: the dot product or scalar product always results in a single number, not a new vector. So, while I cross j gives you k, I dot j equals 0. Second, watch out for the temptation to assume that I dot j equals 1. It is a common mistake to think that because these are all unit vectors with a magnitude of 1, their product must also be 1. But, as we saw in our derivations on slides 4 and 5, the result depends entirely on the angle between them. Since the axes are perpendicular, the cosine of 90 degrees is 0, which brings our result to 0. Finally, pay close attention to how you handle constants. When you are faced with an expression like a I.bi, do not rush. A common error is to lose track of the coefficients. You must first multiply the scalars, a and b, together, and then multiply that result by the dot product of the unit vectors. Following this order of operations will ensure your calculations remain accurate. Now, before we wrap up today's lesson, I want to touch upon some common pitfalls. Even students who understand the core concepts can sometimes stumble on these 3 specific areas during exams. Keep these points in mind, and you'll find that working with standard unit vectors becomes much more intuitive.